Okay, I think we have everyone in the session. So good afternoon and hello. My name is Jeff Matheson and welcome to the Patent Math Conference. In this session, fractions are hard. Here's why and here's what to do about it. Before we start, I just want to remind you that if you are using the conference app, the announcements for this conference are under the Info tab. All announcements for today are also in the conference website, as well as the presenter bios and handouts. And we will place a link to that conference website in the chat box in just a moment. And please note that not all sessions have handouts, but you can find the handouts for particular sessions in that conference website. If you'd like to enable closed captioning, please click on the CC icon on the toolbar. And throughout today's session, if you have questions, please feel free to place those questions in the chat box, or you can unmute yourselves and raise those questions. And Dr. Tanton likes to be interrupted with questions. He wants to be able to handle those in the moment, so please don't hesitate to ask those questions. And now, without any further ado, it's my pleasure to introduce you to Dr. James Tanton.
Well, beautiful. Thank you and welcome, and thank you for having me. I'm actually in Phoenix, Arizona, so it's an honor to be part of Pennsylvania today. So real joy to be here. And I don't see any of your beautiful faces, but I'm going to ask a question nonetheless that might require you revealing yourselves. I want to make sure everyone is aware of one very important piece of mathematics. In fact, this is the only piece of mathematics I really truly care about. Is everyone in Pennsylvania fully aware that there is an international salute to mathematics? Do you know whether there's a math salute or not? Give me a thumbs up or a thumbs down, or, no. Okay, a couple of people are shaking. No. What are we talking about? No. Okay. I'm now duty bound to share with you the international salute to mathematics. And I'm not making this up. So everyone's going to do it with me. Sure, don't have to show your faces, but I'll trust you doing it. It's very weird. Watch out. So you have to put down all your coffee cups and pencils and paper, because you need both hands completely free. And the salute begins as follows. Put your arms out front. Right, for all those I can see, I'm watching. Okay, good job. Then you go right hand over left hand. That's the hard part, right over left. Great. Now you go palm to palm, and then the salute gets weird. You wiggle your little fingers. Then you wiggle your thumbs. Then you wiggle your little fingers again. And then when you're ready, just come on back. What? Uh-oh. Should I do it again? Would it be helpful if I did it again? I got one nod. I will take that as a collective nod for 80 odd people. Okay, I'll do it from different angles, see if this works. Arms out front, so let's try it again. Right hand over left hand, so you see I'm not cheating. It really is my right hand over my left hand. Palm to palm. Great, get those fingers clasped. Wiggle the little fingers. Wiggle the thumbs, wiggle the little fingers again, and then when you're ready, just come on back. Okay, what's going on? What is going on here? Any thoughts, any questions, any worries, any wishes? Magic, it's magic. Interesting. All right, okay, actually it's more than just magic. It is actually mathematical. Yes, I'm doing something that's just like a bit of a gimmick and it's just fun and games, I know, but actually there's a very good pedagogical lesson in this salute. I've actually given you a problem. The problem is, how do you do the salute? In fact, it's a kind of a special problem. You know what the final answer is meant to be. It's meant to be hands like this, untangled. So what's a really good strategy in math and in life? You've got a problem and you think you know what the answer should be. What can you do?
Work backwards.
Work backwards. That is such a powerful idea. It's a very simple idea. It's so simple, people forget about it. But actually, in mathematics, it's a wonderful technique. Let's work backwards. So I'm not quite sure if you want me to give it away or not, but I'm going to just half help you then. I'll compromise, half helping. Let's start at the end and let's see if we can work backwards. Let's see if we can reverse engineer this. And let's see how it feels like. So here's the answer. We know the answer is like this. You have to say, well, where did this answer come from? Well, it must have come from my hands being turned over. Okay. Then you say to yourself, well, where did that come from? My fingers are curled together. That must have come from my fingers being uncurled. And you realize right now, this feels very different and strange. We start at the end, and got to a very funny feeling middle position. That feels very different from probably what you were doing. So here's your challenge. Now half helped. Can you now start at the beginning and say how I get to that same funny feeling middle position? So once you're there, you know you can come back. Okay. So here's the deal. We have 80 minutes left together. You can just, while I'm being particularly boring and dull for those 80 minutes, you can just turn your camera off and particularly practice that to amuse yourself for the next 80 minutes. And if it's driving you really insane, just let me know, and I promise I'll give it fully away at the end of the session if you want me to. Or I won't. If you don't want me to, go for it. Just figure it out for yourself. That is the International Math Salute. I'm not making it up. If you Google International Math Salute, you truly will find this. Okay, so that's the important piece of mathematics done. Now I have to go to the other piece of mathematics I'm meant to be talking about, which is fractions. To do that, let me just share my screen. This always takes a little bit of fumbling. So where is my screen? Great. And share. All right. Are you currently seeing my hands on a piece of paper? Can someone give me like a nods? Yes, excellent. All good to go. And today's topic is fractions are hard. Why are they hard? What do we do about it? And you kind of get a hint already in the picture I drew that fractions are a little bit confusing. I mean, I've drawn some portions of pi here, and well, the thing is, we all do have an intuitive feel for what a fraction is. It is some portion of a pie or portion of some sort of object. The idea of half of something makes a good intuitive sense to us. A third of something makes good intuitive sense to us. But what's tricky is when we have to start doing some mathematics with fractions. And mathematics then gets a bit thorny. For example, if I am thinking of portions of pie, maybe adding a half and a third makes sense. Just take those slices of pie and put them on the same plate and I'll get some sort of answer, whatever that is. Okay, so maybe addition makes sense if I insist on doing mathematics with fractions. But then what about multiplication? Does multiplication make sense? What's half a pie times a third of a pie? That actually makes no sense. That really is nonsensical. I have no idea what half a pie times a third of a pie is. So there's something very confusing going on here. And this is the challenge of early grade teaching of fractions. Yes, we must absolutely help students develop an intuitive understanding what portions of things are, what half means, what a third means, what a quarter means, and how to do some basic manipulations and see them in different contexts. Absolutely good, vital work. But at the same time, the school curriculum wants you to do the mathematics of fractions. And that seems to be the horror part, the part that scares people. There are very few people on this planet say they like working with fractions. It's not because they don't have an intuitive feel for what basic fractions are, it's because of the mathematics of the fractions that gets very thorny and confusing. So what I'm going to do right now is basically go through an overview of how the mathematics of fractions is typically presented to students from early grades all the way through. And I just want to point out the confusing bits. This is, I feel like a little bit bad for doing this because the curriculum is doing good work. It really does develop good intuitive understanding of things and really does make sense and good service to students. But at the same time, we never get the chance after going through 6-8 years of fractions to look back and understand what on earth did we just do? Does it all hang together? And my question is, well, does it all hang together? So let's see what the together stuff is first. And let me go through a very brief, probably disservice to all of school mathematics on the theory of fractions from the get-go. So here's what some very early grade experiences are with fractions. For example, a student might be shown a picture of 6 kittens and asked, can you please circle 1/3 of the kittens? And the student might go, okay, that looks like 1/3 right there. Great, good job. You've got a sense of 1/3 of the kittens. How about circling half the stars? And you circle half the stars. I'm sure you're all seeing it as well. I might do half the stars this way. Great. So there is a sense of fractions that is some portion of some collection, of some whole, or some group. And that's fine. It really is absolutely vital that students understand what 1/3 of something means, what 1/2 of something means, and develop good intuitive understanding of it. And also to know the words 1/2, 1/3, 1/4, and so forth. That's absolutely vital. And there's a lot of subtlety even in this. Because actually, in order to circle 1/3 of the kittens, I had to say to myself, oh, I need 3 equal-sized groups. Because you're probably thinking there's 2, and 2. And one of those equal-sized groups is what I circle and call it 1/3. So that's actually really quite a lot of work there to identify. First of all, you identify equal-sized groups, then the word third means I want three of those, I want three equal-sized groups, and I want to circle one of them for 1/3 to be one of those equal-sized groups. There's a lot to unpack there, and the curriculum does a very good job of that, and it's very helpful and very good. The trouble is, the English language doesn't help here. These are very weird words. I mean, we do say 1/7. If I want 1/7 of something, great, we actually see the number 7. We do say 1/6, so we actually do see the number 6. And I want 1/6 of something, I want one of the 6 equal parts. But then the English language is very unkind. We should say 1/5, and we don't say 1/5. That in the chat, what do we say? What is 1/5? Exactly. English is weird. It says 1/5. Okay, we do say 1/4. Okay. But actually, we're a little bit confusing because we also associate that with the word quarter. So we've got two different words for a fourth. We don't say 1/3, unfortunately. I like saying 3. We don't say that. And we say a third instead. Where's my third gone? Up there. And we don't say 1/2. We should say 1/2, but we don't. We say 1/2 instead. Very, very hard for young students to unpack all that. All right, okay. In fact, there's a lot to unpack. There's so much subtlety here. I could spend probably an hour just talking about just circling a third of the kittens. Because actually, it was really quite complex in this example, because there's actually many equal-sized groups. There's 3 equal-sized groups of 2. Or I could look at the picture and say, actually, it's 2 equal-sized groups of 3. There's a group there and a group there. I can even say it's 6 equal-sized groups of 1, 1, 1, 1, 1, 1, 1. I can even say it's just 1 equal-sized group of 6, 1 block of 6. So the fact that I said third was my mental clue. I was meant to find 3 equal-sized groups and then circle one of them. A lot there. Things might get a little more interesting. For example, a student might be asked to circle 2/3 of the kittens. Okay, so I've brought in some notation here, the mathematical notation of a fraction, so 2/3. And listen to what English does here. English is actually helpful this time. We say 2/3. Like if I said 2 houses, that's a house and a house. If I said 2 llamas, that's a llama and a llama. And I'm actually saying in English 2/3, that would be a third and a third. There's 2/3, absolutely beautiful. In fact, English is friendly to us right now. 3/4 is literally 3 quarters. And 7/8 is literally 7 of those 8s, and so on. So if English can be unkind and English can be kind, a lot to take in for young minds. But here's the thing. If this is my first experience with fractions, I'm wondering, okay, what is a fraction really? Right now, in this context, in my experience as a young student, it's a call to action. I had to circle something. I had to select something. A fraction is just a call to action of some kind. It's certainly not a number. In fact, I wouldn't know what to answer if I was asked right now, what's a half plus a third, James? And I'd say to myself, half plus a third, well, I guess that's 2 kittens plus 2 stars. Nonsense. In fact, you can't even see my pictures. My kittens look like stars. So this is very weird. There's no mathematics here in terms of the arithmetic of fractions. It's just really about this early part of the curriculum. Let's get an intuitive feel for these weird English words and beyond. All right, grand and good. There's no worries. I mean, the real reason I couldn't actually talk about a half and a third together because I'm literally trying to compare kittens and stars. They're incomparable. I can't do that. So the curriculum then does something strange. Well, it makes sense because we've got the story on our heads. It makes an edict. And so at some point in the early curriculum, conversation turns to, all right, we're now going to declare that in any conversation about fractions, the fractions must come from the same whole. Okay, all right, I've heard that phrase a lot, must come from the same whole. This word whole, I've got a question for you. Is that an adjective or is it a noun? What do you think? Noun? Both. Well, that's interesting. Both. Yeah, I could use it as an adjective. I spent the whole day doing math. So it's an adjective in that sense. Or I could use it as a noun in the sense that something like, on the whole, life is good. So I spent the whole day doing math. On the whole, life is good. So it's a little bit weird. It's grammatically now, but it's also naturally. Yes, it's both. So it's a little bit confusing everyday life. And even just saying the whole is a little bit strange in English. It feels a bit odd. So this language just has slight weirdness to it. That's okay. We can deal with that. But I've got to be very clear what I even mean by the whole. I just want to point out English is challenging. So what people tend to do, and you see this over and over again, that the curriculum tends to choose a favorite whole. And that whole is what I've already been drawing along all along is pies. People tend to say, let's make the whole a pie, which is fine. Pie can now be our wholes. That's great. All right, so that's all good and grand. So we might be slicing pie from now on. So let's divide a pie into, say, 5 equal parts, if I can draw that very well. All right, so there is a picture of a round pie, to the best of my ability, divide it into 5 equal parts, and my camera's there. My camera's now focused, which is great. And I might be asked to select 2 of those fifths. Great, that's great. Brilliant, brilliant, brilliant. But I'm going to be honest here. Kids are like lawyers. They like to find exceptions and loopholes to things, which is absolutely perfect. That's absolutely perfect, because that is mathematical thinking, really thinking deeply about this sort of stuff. The key thing is you're meant to divide the slices into the parts into equal slices. What does equal mean? Example, if this was an anchovy pie, an anchovy pizza, if this piece happened to have 7 anchovies on it and most of the other ones only had 1 or 2, this piece for me is way more equal than any other piece. I like anchovies. I will say that's the coveted piece. Those pieces aren't equal at all. That's the best pizza of all. Whoa. Or I could say this. Let me divide this pizza into 3 equal pieces. Here goes. Great. Can you find me a context where that is a valid answer to dividing that pizza into 3 equal pieces? Who might think that's 3 equal pieces? No, people shake. I mean, people just like turn the cameras on to shake their heads at me. Okay, context matters. Suppose I and my friends love cheese stuffed crust. We don't care about the topping. All we care about is the crust. In which case, if I drew it kind of correctly, I would say, yeah, I don't care one word about the topping. I'm going to throw out the topping. That piece looks just as good as that piece. This looks just as good as that piece. There's an implicit assumption that we're talking about the area of the pizza, not the crust. That perimeter doesn't matter. So we should be very explicit about that, because there actually could be 3 equal pieces if you only care about the crust. Okay, a bit weird, but I'm pushing it. I'm being like a kid. I'm playing like a lawyer. Find exceptions. Actually, if my pizza was really a cake and it was a square cake, I can get into even further trouble, because I suppose I want to divide this into 9 equal pieces. Here's a nice chocolate cake divided into 9 equal pieces. I wouldn't consider those pieces equal. Which piece do you think, can you guess, I would go for if I get to choose any of those 9 pieces, because it's the more equal than others? Yes. If you're like me, I like the icing. I want the side icing too, please. So yes, there's all sorts of issues. Corner pieces are more coveted than middle pieces. I mean, that piece in the middle is, whoa, not worth my while. I want the icing. Context, kids will always do this. They'll always find context. It's fabulous. They absolutely should. I love it. But what we need to do is be explicit that when we're drawing these pictures of pie, we are assuming that the pie is a uniform topping that doesn't change across the pie. We're assuming we don't care about the crust. The perimeter is 0 interest. We're talking about the top surface area. That's all we're talking about. But even then, there are some subtleties. If I drew such a pie, here goes. I'm going to draw a square pie this time. Everyone draws round pies. Let me draw square pies. I will assume it has a uniform topping. I'm going to divide it into 4 equal pieces. Here goes. Assuming my picture is accurate, would you agree they're 4 equal pieces or not? Have I divided that pie into quarters? Yes. Okay, lots of people saying yes. All right, so, okay, this is actually subtle. So kids would need to have a good understanding of area in order to answer this question, because yes, if all I care about is the surface area of this pie, or the area of the shape, then actually each of these is a part of the area. So the other issue is, no one says the pieces have to be congruent. Pieces don't have to be the same shape. I mean, I know we always draw pictures like this, where the pieces are always the same shape. We can't forget, we don't care about the shape actually of the pieces. All we care about is the fact that they have the same area. In which case, students should have a very strong notion of area to really be able to take this in properly. And yes, this is a big struggle. This is a big struggle. You can even come up with simple places like if I took a triangular pie where all the pieces are actually congruent, but they could be just oriented differently. Even that can be a struggle for students. Have I divided my triangular pie into 4 equal pieces? The fact that one triangle is upside down from the others can be an issue. I totally get that, and every right to get it. Fractions are hard and subtle. All right, so this is, so yes, so what grade level am I at? I'm basically going kindergarten all the way up to grade 6, 7, 8, whenever they stop teaching fractions, because I know in high school, which is my background, you don't teach fractions anymore. You just say, kids, you're on your own, you've got fractions, go for it. So my point is going to be this: as I go through this overview, just be beautifully honest as your own adult self that there are subtleties and confusions here, and be equally honest with your students. Have these conversations. Do have them talk about being like a lawyer. What do you do with pieces that aren't the same shape? Is that triangle the same shape as that triangle there? There's lots of great conversations here, and they're all subtle points about doing this. Yes, you've got to get in and just do it. Curriculum asks you to do it, but there's lots of subtlety here. But the fact is, now that we're talking about the same whole, that we're always talking about a pie, then it looks like we can legitimately start doing arithmetic on fractions. For example, here's half a square pie. Here's a quarter of the same square pie. So what do you think, except my camera's being naughty, give me. What do you think I would draw as my picture for adding a quarter and a half? Yeah, so what you physically imagine doing is taking that portion of pie, plopping it on the plate over here, and on the same plate, add that quarter of the pie. Now, it might be confusing where I put it. Maybe just put it up here instead. Great. And there's the answer. The picture of the answer is addition just means put the slices on the same plate. Literally put them next to each other. Now, you're right. You might have to go further in your curriculum and say, kiddos, I'd love you to see if I just drew a line there that actually this looks like 3 quarters. Okay, that's fine. 3 quarters, because there's 1 quarter, another quarter, and another quarter. 3 of those quarters. Okay, that depends on where you go with the curriculum, but that's great. Addition, kind of starting to have a feel. We can now legitimately start adding things because we're now working with the same whole. I still don't know what multiplication would mean. I still don't know what half a pie times a quarter of a pie means. That's just really, I have no idea how to think about that. No idea what that is. But at least for addition, we're making some headway. Fractions are starting to feel like things we can do arithmetic with. Okay, great. Actually, let me just have a little pause. I've been rambling in this fast speed, going through everything. I don't know if you know about the jargon of fractions. So the word fraction itself comes from Latin. I never took Latin. I know how to say it. Fractionem. Does anyone know Latin? Could you unmute yourself and correctly pronounce this word from late Latin? None of us know Latin. Okay, how do you pronounce this word? It comes from the word fractionem, or something like that, which means to literally the act of breaking something into pieces. So it does sound like a Harry Potter spell. So people actually did think about breaking things into pieces, and that led to our word fraction for part of the pieces. Great. And I've been saying all along, things like 5/7. English is very helpful here. 5/7 would be 5 copies of a 7th. Great. And then we have words. Numerator for the top number and denominator for the bottom number. It's really interesting that the word numerator comes from, again, late Latin, numerare, I'm not sure how to say that, numerare, which actually means a count of things. This means a count of things. And the denominator actually comes from a compound Latin word, de nominare, or something like that. And de means complete, We put a prefix day on things, it means complete. And this means nominare means to name. So what we got here, the numerator comes from the word means a count of things. Oh yeah, I counted 5 copies of a thing. And what's the thing I counted? What type of things I count? It was a 7th. The complete name of the thing I counted was a 7th. Hence the name numerator, the count of things, 7th, the type of thing I'm counting, denominator. There it is beautifully. In fact, we do have other words for counting. For example, to enumerate means to count it all out. So that comes from numerare as well. And a denomination. You often hear different types and classes of things called denominations. What denomination are you? Really is what type of thing are you, from the same word there. All right, so there it is. There's a little bit of jargon of fractions. But, where are we? Where are we in the strange story? We had fractions were parts of a whole. I could circle some kittens. I could circle some stars. And then we said, okay, no, we need to make this wholes the same so I can compare them. I can't compare kittens and stars, but I can compare portions of pi against each other. Great. That's all starting to make sense. And it feels like I can start doing some arithmetic with fractions by putting bits of pi together. But then something else happens in the typical curriculum. People start talking about one of these things, a number line. Okay, so I'm whipping through the grades now. So somewhere along the story, students are introduced to this notion of a number line. And how this number line works is you take a stick of length 1, there it is, and just lay copies of it end to end, starting some beginning point. Beginning point's always labeled 0, and just go across as far as you want. All right, and then we'll label points on the number line. For example, this 4 here is labeled 4 because going from here, the start, I laid 4 sticks across, and that reached me to this position. I'll label that 4. To get here, apparently I need to lay 6 sticks across to get me here, and only 1 stick across got me there. And actually kind of calling that 0 now makes sense because I label no sticks across from there. Where will I be? I'll be right there. 0 sticks is there. So there's the notion of the number line. All right, so that comes up in the story of early mathematics. It's really interesting, by the way. The notion of a number line was a late invention in the history of mathematics. I believe it was John Wallace in the 1500s, even 1600s, I think it was, maybe 1600s. Not until the 1600s, someone thought to put the numbers in a line. That notion that seems so fundamental and basic to us was not needed in mathematics at all until very late in history. People thought, actually, we could do this and have a visual arrangement of numbers. Grand and good. All right, but then, okay, here's what the curriculum does on the story of fractions. Okay, so if we've got a number line, let's now make our stick of length 1 is now our new pi. They say, make the stick the pi. Okay, so I'm now going to think of pi, not as a round pi, not as a square pi, but as a very thin, flat, linear pi. That's my new pi. In which case, a half would be half a stick. It would be half a stick and not the rest of it, and so on. And a third would be a third of the stick. So now we're doing the same ideas, but now our pi is a stick. All right, which means I could lay portions of sticks across the number line as well. For example, if I take this half a stick, I'll do it in black so you can see it on the picture here, lay it from the start, I end here. So what people say is, okay, we might as well label that point the end of half a stick. Let's label that point 1/2. Okay, that's great. If I did something more complicated like 7 halves, what would that be? Well, if I go back to my thinking, that's 7 copies to count, numerare, 7 copies of the type of thing I'm counting, denominator, half, 7 copies of a half. In which case, okay, there's 1 copy, 2nd copy, 3rd, 4th, 5th, 6th, 7th. And bingo, I ended up here. I'll label that point 7/2, 7 halves. Great. So now we're starting to draw numbers on the number line. And this is, I don't know if it's a psychological ploy, but it feels like it's a bit of a psychological ploy. Before this, fractions were pieces of pi. There are portions of pi, portions of a whole. We're now labeling points on a number line as fractions, which is subtly suggesting, oh, if fractions are on the number line, maybe fractions actually are numbers. Okay, maybe fractions actually are numbers. There's no reason to think that. We're just suggesting it. It's a little psychological suggestion here going on that maybe because fractions are on the number line, maybe they're numbers. And we even reinforce that idea by doing some arithmetic on the number line. See if I can do it very well. Let's try something like 2.5 plus 1.25. I'm going to make my picture very messy now. Let's see if I can make sense of that on my number line. Because if fractions are numbers, I should be able to do addition. Well, the typical thing to do is just resort to what I did before, which is, okay, it's a length to, oh, there's a bad pen, that's not working. Give me, let's get a pen that works. 2.5, 1, 2.5 will get me there. Okay, that's a bad pen as well. James, find a good pen. Try this pen. There's 2.5, and if I'm adding to that, I guess adding means lay end to end out of the blue. Let's do 1.25 sticks. 1 stick and 1/4 seems to land me there. Maybe that's the answer to 2.5 plus 1.25. And maybe I can figure out that's like 3 3/4 mark, something like that. All right, but my point is, the curriculum does a switcheroo on kiddos at some point. Fractions are now portions of sticks. Our pie is now a flat little pie. It's not portions of pie anymore. It's now portions of sticks, actually with the suggestion that really maybe fractions are numbers. Okay, a little bit slippery, because now we're asking kids to think of portions of a whole, portions of pie, and numbers. Which of them actually is it in the end? Which of those things are we actually doing in the end? All right, then in this whirlwind story come the later grades, where another edict is made. Here's the new edict at some grade level. Fractions truly are numbers. I'm going to tell you fractions are number. And I'm going to tell you what type of numbers they are. They're actually answers to division problems. All right, so fractions are numbers. So goodbye parts of a whole, goodbye portions of pie, goodbye lengths of stick on a number line. Now those points on the number line are actually the fractions. All right, but there's something confusing here. They're answers to division problems. Okay, if I actually think about that, I'm really confused, because 7/2 means 7 copies of 1/2 in my old way of thinking. But now I'm told, no. 7/2 is not 7 copies of 1/2. 7/2 is now something different. It's the answer to a division problem. It's the answer to 7 divided by 2. That's what 7/2 is. And my question now, are these the same? I mean, first of all, in what sense could they be the same? And if they are the same in that sense, are they truly the same in that sense? All right, how many people have I lost? Is anyone with me? Do you think 7 copies of 1/2 and 7 divided by 2 should be deemed the same? Or are they different? The chat is open. The same. The trouble for us adults is really, really hard to let go of what we already know and get back in the mindset of a student, because this is actually a subtly very hard question. Because let me see if I can figure out explain why this is hard, if I can find more colors. Here goes. Let me draw that number line again. 0, 1, 2, 3, 4, 5, 6, 7. I'll go up to 7. We had 7/2 at one point, which was 1/2 and 1/2, 1/2 and 1/2, 1/2 and 1/2 and 1/2. They got me there. So that's what this means in our old way of thinking. Now, in our new way of thinking, we're meant to take the number 7 and divide it by 2. All right, here's the number 7, which I guess the number line. It's not clear, actually, if number lines are points on a line or they lengths along a line. That's another confusion I have. And now I'm meant to chop that 7, that whole length of 7, into 2 equal parts. I guess what divide by 2 means. And my question is, are these lining up? Was a little bit of space between them? Are they exactly the same? My point is, it's very hard to see. That it's subtle, and it takes some thinking to justify what I'm seeing in the chat, why 7 copies of 1/2 really is the same as taking 7 and chopping into 2. I go, why is that one big chunk on the left equal to these 7 little chunks below them? There's something to think through there. Yes, and they actually sound different. I'm doing different physical processes here. That's one physical process. That's a different physical process. And the claim is they're always going to end up in the same place on the number line. There's a lot to think through here. A lot to think through is my only point. There's a lot to think through. I mean, we can make it worse. 2/3 is 2 copies of 1/3 in the old thinking. And in the new thinking, 2/3 is the answer to taking length 2 and dividing into 3. What sort of picture would you draw to justify, prove, convince, I don't know what the word is, that that's the case? Yeah, silence is a lot. It's subtle. It is subtle. There's something to think through here. 0, 1, 2. All right. If I took a length of 2 and divide it into 3 parts, okay, 3 equal parts, be something like that. Pretty rough. There's one of those parts, another one of those parts, another one of those parts. All right. Is that 2 copies of 1/3? I know, this is getting confusing. My brain is hurting. That's the only point I want to make. My brain is hurting. Brain hurts. This stuff is actually extraordinarily subtle. Now, most people say, sure, James, just do 1/3 and 1/3, and you'll see you'll land there, which is actually 2 copies of 1/3. Read the same as one of the sections there, which was 2 divided by 3. Everything lines up beautifully. Whoa. Sure, that looks convincing. I still have to think deeply, personally, about what that really means. My brain keeps hurting. It keeps hurting. All right. I'm going to keep going with the muddledness, because then things get really scary, at least for me. For example, at some point, the curriculum will talk about equivalent fractions. And they may have talked about the number line already. They may have talked about this and that. But here's the funny thing. Often the curriculum, whatever textbook you're using, will say, no, we can use pi. It's okay to use pi for fractions, even though we just told you we can't do that anymore. No, I can show you fractions are equivalent by drawing some pi. For example, here's the fraction 2/3 drawn as a rectangular pi. Great. Now, I could be sneaky and say, okay, I'll take that picture. And what I'll actually do is let's get some green pie here. I'll slice each of those pieces in half. And suddenly it looks like, oh, I've got 4 pieces out of 6. Or I can slice the pieces into thirds instead. Okay, so here's my original picture of 2/3 of a pie. Divided, slice into thirds. I'm being a bit naughty, doing it this way instead. And say, oh, it looks like I got 6 out of the 9 thirds. These must all be, they're the same picture. These must be the same fractions. Okay, that's wonderful. That's beautiful. I'm thumbs up for pictures like this. There's nothing wrong with pictures like this. This is great intuition for what's going on. Except when do we do it? If I've just been told that I can't think of portions of pi anymore, then why do I have the right to go back to doing portions of pi? The curriculum will often bounce back and forth without notice of which model it wants to use to justify different things. This often happens when we start talking about equivalent fractions. I thought I was talking about points on a line, but now I'm talking about pi's again. What's really going on here is the question left in my mind. But then, sorry, it gets even worse. It gets way worse. I mean, this sort of statement, 2/3 of 4/5. Now, if I'm allowed to keep thinking about pi, and now I'm not sure if I'm allowed to as a student anymore, I'm allowed to keep thinking of pi, I can make sense of this. I can make sense of this word of 2/3 of 4/5. There should probably be another word there, but since we're talking about the whole being a pi, it's implied we're talking about 2/3 of 4/5 of a pi, if I'm allowed to talk about pi. It's so much easier to draw square pi. Let me draw square pi. I can do 2/3 of 4/5. I'll start by drawing 4/5 of pi. There it is, 2, 3, 1, 2, 5. There's fifths. So 4/5 would be this left 4 sections. Great. Now what I want to do now is take this 4/5. I should actually count them. 1, 2, 3, 4/5. There they are. Now I want 2/3 of just those 4/5. Okay, I'll divide that section, that green stuff, into thirds. And now I want 2 of those thirds. And I can see I've got this. Great. Lovely, 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 lovely. Great. And now I can say, okay, 2/3 of 4/5 of my pie, the implied of my pie there is that orange stuff. And if I'm really, really astute, I can say, look, if I just imagine drawing those lines a little bit further there, I can see I've got 8 pieces out of 15 pieces. So the answer here is 8/15. And I say to myself, great, the word of, I get the word of. The word of makes sense. I can draw it out and get the answer. All right, warning, warning. I've seen this so many places. The curriculum gets weird. And they say, oh, look, you just happen to draw a square pie. How fortunate. If you drew a round pie, I wouldn't know what to say, but you drew a square pie. That's luckiness number 1. You'd happen to draw a square pie. And it looks like you took a very thin pie here, a thin linear pie, and just worked out 2/3 of it, this part of it. There's 2/3. And it looks like you took another thin linear pie and earlier worked out this part of it. 4/5 of it. And doesn't this look like the area model for multiplication? Just looks like the area model. So surely this pink stuff, which also looks like an area, must be this length 2/3 times that length 2/3, 4/5. And what's my answer? Well, you just told me it's 8/15. Suddenly people say of means multiply out of the blue. And I really, truly struggle with this big time. Because it was luck I happened to draw a square pie. Could you do this with round pie? Could you convince me that 2/3 times 4/5 is going to be an area thing with round pie? Good luck. I don't know how you do that. But more importantly, what's going on philosophically here? If I am allowed to go back to thinking about pi, I was told strongly, you must use the same whole, must be the same whole. In which case, if whole is pi, I must be doing it with the same pi. Look what you just did to me. You did a flat linear pi there, and you did a flat linear pi there. Okay, they're the same pi. But then you said my answer is really back to being a square pi. You've got at least 2 different pies in that picture. You're not doing the same whole. Therefore, why do you have any justification doing this? And why, just because it happens to look like the area model picture for multiplication, why don't you suddenly say, oh, because it looks like it, it just must be? I truly struggle with that. I have a hard time. I just don't know what's going on. Why does of mean multiply, other than it's coincidental the picture looks like it's the same? Good luck, good luck. I admire educators at this age level of teaching, because this is muddled. This is deeply muddled. And sure, we can just tell kids, you know, of means multiply and just push our way through. If your curriculum is a little bit bold that way, it does it. Okay, kids will get their answers to their problems. But for any deep thinking kid, like most adults and kids on this planet, they really thought about this. This is all over the place, right there. And you know what? It gets even worse. The worst, the even harder one would be this. What do we often tell kids? What do lots of curriculum or books or people say to do with dividing fractions? Meanwhile, I dropped the pen, so I'll get back and get my pen. Flip the second. Then multiply across. Yes, yes. You hear this all the time. What is it? I think it's called the KFC, but it's not KFC. It's KCF thing or something like that. Keep, change, flip. Someone did it. Keep, change, flip. Sure, okay. What they mean by that is keep the 2/3 the same, change this operator from division to multiplication, and flip the fraction. Whoa, then work out this. Oh, then pull this of 2/3 of 5/4. Work that out, and then apparently that's your answer to dividing fractions. Whoa, okay, this is these big red pen. Okay, if this was mysterious, if I actually sat down and thought about it, this is down outright bizarre. Why would dividing fractions correspond to that? Yes, there's techniques. I'm seeing common denominators. You can do all sorts of stuff. I mean, actually, you know fractions, this is the same as 2 divided by 4 over 3 divided by 5. Whoa, there's all sorts of things you can do. Deeply mysterious, deeply mysterious. So now we have the challenge. If we want to be truly honest with our students, we teachers have a mighty difficult challenge. So much of the curriculum tends to be very muddled, bizarre, and a mishmash. We tell kids at one level, you must have the same whole, and then we violate that ourselves. We tell kids that fractions are actually points on a number line that answers division problem, and then we violate that ourselves. We say, no, don't go back to the pi model, then we'll always go back to the pi model to justify things. There's really, really terrible confusion to be had here. And it's very hard for an adult teacher to actually do the right thing by kids, get them something to hold on to with the mathematics of fractions. So that's what I've been thinking about very deeply for a long while. You can see I've just spent the last 40 minutes prattling on in my fast-paced way with my funny accent, just giving an overview of all the muddles I can identify in the typical textbook experience. Now, I do actually believe in those typical textbook experiences in the sense that they are doing beautiful work developing the intuition for fractions and the physical reality of fractions, and that's good. Thumbs up for me for that. All I ask is a sense of frankness and honesty. All these different models of fractions, if you're talking about proportions of pi, great, that speaks some truth about fractions, it certainly speaks some intuition of fractions. If you're speaking about fractions being numbers and answers division problems, that's great. That also speaks truth about fractions, some partial truth about fractions. If you're speaking about points on the number line, no worries, that's also speaking truth. But none of these models are speaking the whole truth. And we can tell kids that. We have some physical intuition of what a fraction is, and we see different places where fractions come up, and different contexts that come up in different ways. And there's something going on. What's the one big unifying story to all the fractions that brings all this together? Because the curriculum will never step back and say, hang on, we had all these different ways about thinking about fractions. What are they all saying collectively? What's the whole one truth rather than a whole collection of partial truths? And the reason I got on this kick, because my background, unfortunately, is not your grade levels 3 to 6. I admire your work tremendously. I just became a high school teacher. When I left the university teaching, I became a high school teacher. And everyone in the high school world seems to complain that kids cannot do fractions. I personally don't blame them. If I don't know what to hold on to, if I had this story I just went through as a kiddo. And yet high school teachers say, but it's not our job to teach kids fractions. And I thought that was terrible. Of course it's our job to teach kids fractions. We all should be teaching kids fractions because fractions are hard. So I would actually teach my high school students fractions, like all the intuition you build up and all the beautiful ways the curriculum does do well, it does really well. Let's be honest, every one of those models speaks partial truth, and kids can handle just seeing part of a picture and knowing it's only a partial part of the picture. So what I'd like to share with you now is what I did with my high school kids to say, okay, let's go back through all this stuff and see if we can make sense of it once and for all. Now, my challenge is I'm doing this from the perspective of an adult now, of someone who's been through the curriculum experience and coming back to revisit it. So how this helps you in your teaching practice, I'm sort of leaving it in your court, unfortunately. I'm going to give you an adult experience of a way to think about fractions, and I'd like you just to personally mull on it, so that when you see something in your curriculum that is a little bit challenging, and as you say, it's bouncing around between models, maybe you'll have a way to speak about it frankly and honestly with your students, what's actually happening. It's okay to bounce around by models, just be clear that you're doing that, because we're trying to pick out portions of truth from different ways that we experience fractions in the real world. So I've left myself just under 27 minutes to try to make fractions make sense. But I feel like we need a little break. I'm willing to give 20 minutes of it. Can we have, say, a 3-minute break right now? Everyone can just get up and stretch their legs, go fill up their coffee mugs, go get a glass of water or something. Can we come back in 3 minutes and I will reveal to you what I did as a high school teacher to help kids see fractions in a way that was unifying and meaningful to them. Does that sound like a plan? I mean, the answer has to be yes. See you at 7 minutes past the hour, okay? I'll be back too. Well, I'm back. Hope everyone else is back. All right, so where do we leave off? We left off with me sharing my screen, which I should do again. Where's my shares? There it is. And within that, close that, hang on. Share, there we go. Within that, we left on this brain hurty part. Fractions are brain hurty. We've got this wonderful, wonderful story, which is great for developing intuition. The intuition only speaks partial truths, left, right, and center. We don't yet know what the whole truth is. What is a fraction really? What's really going on? The mathematics of fractions. As I said earlier, I came into the high school world and said, okay, what could I do for my high school students to help them really see their previous experience of fractions in one unifying whole? So without further ado, because I've been making a little lead up to this, let's talk about the approach I did with kiddos that were trying to make sense of fractions once and for all. And I'm going to go with an idea that did come up earlier. I'm going to say that a fraction really is a number. A fraction is a number. Say it up front. A fraction is a number. In particular, it's a special type of number. It really is the answer to a division problem. Now, it turns out there's several ways to think about division, actually, that the notion of division is subtle. So I'm going to be explicit. I'm going to talk about sharing. I'm going to say a fraction is an answer to a sharing problem. So it's a number that's an answer to a specific type of division problem, a sharing problem. And here's what I'm going to do. I'm going to do something like this. Suppose I have 6 pies. Here's 6 pies. And I want to share them equally. So my camera is being a bit naughty. Okay, maybe it's okay. Equally amongst 3 people. So here's 6 pies and 3 people. Now, if I were to share them equally amongst the 3 people, how many pies per person would that be? Well, I can see it equally, give 2 and 2 and 2. Equal sharing of pies is 2 pies per person. But here's the thing. Since I'm saying a fraction is an answer to this division problem, I'm going to write this answer in fraction notation. I'm going to write 6 pies for 3 people is 2 pies per person, where the top number is the number of pies, bottom number is the number of people, and the amount is the amount of pie per person. That's it. I'm literally picking up where school went off. School loves pies. I decided to go with pies as well to match it up earlier. And I did what school says, a fraction is a number. Yes, it is. I agree. And it's actually answered a division problem. I've just now clarified what division I'm doing. It really is equal sharing division. Grand and good. And I can write other things. For example, I gave 20 pies for 5 people. That would be 4 pies per person. Great. Or if I had, I don't know, 7 pies for 1 person, guess that one lucky person gets 7 pies. All right, but to show you how this actually does match up with previous thinking, let's look at this problem. 1 pie for 2 people. If I had to share 1 pie, there it is, equally among 2 people, what would I physically do? How much pie per person is that? Well, you would physically chop that pie in half and make sure 1 person gets half a pie. There it is. So actually, the answer to sharing 1 pie to 2 people is half a pie, which is exactly what we did in early grade mathematics. A half does represent half a pie, the result of sharing 1 pie equally amongst 2 people. And the same way, 1 pie shared equally amongst 3 people, okay, what would that actually be in this little model of pies per person thing? Well, if I've got 1 pie equally for 3 people, I guess 1 person gets what I used to call a third. There it is, a third of a pie, just like the pictures I was drawing earlier on. So I'm sharing pie to match it up. This one's interesting. We said earlier that 2/3 is 2 copies of a third. I've got 2 pies to share equally amongst 3 people. There's 3 people, there they are. How much pie per person is that? I've got very blobby people. What would you physically do? Think about what you would physically do to share 2 pies equally amongst 3 people. And one thing you might do is divide each pie into 3 equal parts and make sure each person gets 1 slice from this pie and 1 slice from that pie. So yes, this person will get 1 slice and will get a second slice. This person will indeed get 2/3 of a pie, what we call thirds earlier on. That person now getting 2/3 of a pie. This is matching our earlier mathematics, which is great, All right, so there's my pies per person model. It matches up with early pie slicing thinking. And we can start developing some mathematics for this. For example, we've already seen that 7 pies for 1 person is going to be 7 pies for that lucky person. And 200 pies for 1 very lucky person, or maybe not lucky, maybe it's too many pies, camera, would be, if you think about it, 200 pies for 1 person, a little bit tautological, would be 200 pies per person. In general, we've got a little property that if I've got A pies for A people, that's going to result in 1 pie per person. I don't know what number A I'm talking about, 1 pie per person. Great. Well, there might be some qualifications in the number A, but for now, this is good. Another thing I could do I can recognize if I had, say, 5 pies for 5 people. You know, you can imagine the picture in your mind, 5 pies to be shared equally amongst 5 people. And to actually do that, you can see in your mind's eye, that will be 1 pie per person. Oh, so what am I doing? No, what am I doing? Sorry, geez, I'm ahead of myself. A pies for 1 person is A pies per person. And now I'm doing this one. A pies for 8 people will be 1 pie per person. Forgive me, I was ahead of my brain was ahead of myself. 5 pies for 5 people, that will be 1 pie per person. 7 pies for 7 people, 1 pie per person. 200 pies for 200 people, 1 pie per person. Grand. Sorry about that confusion. Silly, silly me. That's great, great. We're starting to get some sense of things. Actually, because I like to have fun with mathematics, let's get quirky. I know I shouldn't do this right now, but I'm going to be naughty. 1 pie for half a person. Whoa, whoa. Here's 1 pie. I'll draw a person, but I don't actually want the person. I want half a person. The question is, how much pie would a whole person get? And you think about this for a while and say, okay, James. There's the bottom half a person. If it's 1 pie for half a person, that bottom half gets a pie. Oh, the top half is also a half. Oh, if it's 1 pie for half a person, that top half gets a pie. That means the whole person is getting 2 pies. I'm just being quirky. I'm just pushing the model, just being a little bit naughty. I shouldn't be doing this, but I'm doing it. But it's fun. Example, what's 4 pies for 1/3 of a person going to be? Just really push this model. Can you see in your mind's eye what that's going to be? Here's a person. Third of a person gets 4 pies. Yeah, 1, 2, 3, 4. That third gets 4. This third gets 4. Yes, that's 12 pies for a whole person. Yeah, I'm just being naughty. We shouldn't be doing this. I shouldn't be chopping up people this way or talking about fractions of other people, but just to have fun, we can actually get quirky. In fact, let me keep going. I started today with 6 pies for 3 people. 6 pies for 3 people was 2 pies per person. That's great. That was 2 pies per person. Suppose I'm feeling generous and I want to double the amount of pie everyone gets. See, in 2 pies, I want to double that. How would I actually double the amount of pie each person gets? What would I physically have to do? Well, if I want to double the number of pies everyone gets, I better dish out double the number of pies, because then I'll get double the number of pies per person. And let me just write down what I just said mathematically. To double the amount of pie per person, please make it 12 pies instead that you're giving out, double the amount of pies. All right. Suppose instead of doubling the number of pies per person, I want to triple the number of pies per person. What I physically do, I would triple the number of pies. Triple the number of pies. That is, to triple the amount of pie per person, triple the number of pies. Make it 3 times 6, make it 18 pies per person. If I want to give everyone 100-fold the amount of pies, scale everything up by a factor of 100, then I'd probably have to say, okay, if I want to scale everything up by a factor of 100, that was at 6 over 3, I better give out 100-fold number of pies. This looks like another property to me, another property of fractions. I'm going to write abstractly. I know I'm writing in algebra language, but all I'm going to do is sort of copy this idea. You want to scale the amount of pie per person up by some factor. I called it k. Maybe you want to double it. Maybe you want to triple it. Maybe you want to 100-fold it, centuple it. Then all you have to do is scale the number of pies you're giving out. Scale the number of pies you give out by that same factor k. So that is either double the number of pies, or triple the number of pies, or 100-fold the number of pies. There is another key property of fractions. So this is what I'm saying. I'm just going through this fast, I know, but I'm just playing with my model and saying, what is it saying about properties of fractions? It's saying things like A pies for 1 person is A pies per person. A pies for A people is 1 pie per person. And then I've got this weirder one that if I want to double the number of pies per person, just double the number of pies. I want to triple the number of pies per person, just triple the number of pies. It actually makes sense, even though I written now scary looking high school algebra. Okay, but the ideas are there. So don't use algebra necessarily. Lots of examples are the same as algebra, really. Let me point out one more thing. And this is the key result. This is the biggie. This is the bougie of all the results. Let me go back to 6 pies. Now we're looking for 6 for 3 people. 6 pies for 3 people, that's 2 pies per person. 2 pies per person is 6 pies for 3 people. Suppose I did this. Suppose I double the number of pies and double the number of people. Have I changed how much pie per person there is? I double the number of pies and I double the number of people. Is it still the same thing as 2 pies per people, per person? Yeah, 2, 2, 2 there. And again, 2, 2, 2 there. It's still the same thing. Yes, the same as 12 over 6. 12 pies for 6 people. Or what if I triple the number of pies? Here's triple the number of pies and triple the number of people. It's now going to be 9 people and it's now going to be 18 pies. Is there still 2 pies per person? If I tripled instead, tripled and made this 18 pies for 9 people? Yes, you can just see it's still going to be the same number of pies per person. In fact, I'm now seeing if I multiply this up by some factor like 7 and 7, like 7-5 the number of people, 7-5 the number of pies, it won't change anything. If I centupled, went up by a factor of 100, it won't change anything. In fact, I'm seeing right now that if I change the number of pies by factor k, and I change the number of people by some factor k, then that actually doesn't change anything. It's still going to be the same amount of pie per person. Whoa, whoa. I've just discovered equivalent fractions in this pie per person thinking. This is crazy. This is crazy. And that's it. That's all the mathematics there is to fractions. All of fractions boils down to these 3 ideas, 4 ideas. I can't count. I'm getting tired. Forgive me. All right. All of the mathematics of fractions is encapsulated in this, and all of these properties can be well explained, well justified by using pies per person. And let me show you. Let me show you. For example, we do like to believe that 2 copies of a half makes 1 whole pie. Now I'm going to be a bit sneaky. I'm going to try to be a mathematician now. Okay, my intuition says that should be 1 whole pie. But if I'm going to be a strict mathematician, can I get that answer just by using these ideas? And right now, my brain says I've got 2 times a fraction, makes me think of number 3. I'm going to literally copy number 3. If I copy number 3, 2 times 1 over 2 would be, okay, to double the number of pies per person, double the number of pies. Okay, so it'd be 2 times 1 over 2. Great. With normal arithmetic, I know that 2 times 1 is just 2. That's ordinary everyday arithmetic. No fraction arithmetic there. So that's really 2 over 2. And what's 2 over 2? My property number 1, that is indeed 1 whole pie. Yes, my intuition that 2 halves is the same as 1 actually does follow as a consequence of this mathematics. I can do another one. I remember as a kid when I was being taught things like 7 times 3 sevenths. Just cancel out the 7 and the denominator and the number. Multiplying by the denominator just cancels out. I was told the answer should be 3. I remember, this is literally back in Australia. I just did that because I was told to do it. I didn't understand why. My question now is, could we be mathematicians and see how that's actually also a logical consequence of all this? Let's do it. Here goes. My brain's going straight to this one. To septuple the number of pies per person, just septuple the number of pies you give out. Okay, make it 7 times 3 pies on the top, times 7. Now, this is a little bit weird. I know I'm very tempted to cancel out those 7s because I've been so well trained through my schooling. Cancel out 7s. I want to make sure I'm really following the 4 principles I have on the page. Here goes. I'm going to be a little bit sneaky. This is an epiphany. This is a flash of insight. Rewrite the 7 on the bottom as 7 times 1. Because as soon as I do that, 7 times 3 over 7 times 1, those 7s are immaterial. That's the same as 3 over 1. That got me over the little hump there. And 3 over 1, I was told, is 3 by property 2. There it is. Yes, what I was told as a kid, just go to get that, is actually correct. But I wasn't taught anything that was incorrect in my school days. It was all correct. Whoa, whoa. Okay, last 2 minutes. Let's divide fractions. Let's go for the key one, keep, change, flip. What's going on there? 2 1/3 pies for 4 1/3 people is horrible, I don't even want to draw it. 2 1/3 pies for 4 1/3 people. Okay, here's my instinct as a mathematician. I don't like that. Let's see if I can pinpoint what I don't like about it. I don't like having fractional pies. I don't like having fractional people. That feels wrong to me. In fact, mathematically, that feels very confusing to me. I don't want to deal with it. So my next question as a mathematician, can I not deal with it? Can I make my life easier for myself? What can I do to make this problem easier? And I realized, oh, I just know if I multiply by 3, like 3's cancels what I was taught. Let me triple the number of pies and triple the number of people. By our property, which one was it? Yeah, that won't change anything. Tripling the number of pies, tripling the number of people doesn't do anything. So let's do that very carefully. 2 1/3, there it is, and I triple everything, and 4 1/3, and I triple everything. Yes, I'm using a little bit of a algebra here, forgive me. But I can say, oh, it's just 2 tripled, that's 6, plus 1/3 times 3, 1. Now on the bottom I get 4 tripled is 12, plus 1/3 times 3 is 1. This is the same as sharing 7 pies amongst 13 people. Okay, I still don't know what the answer truly is, but sharing 7 pies amongst 13 people seems to be much simpler than trying to share 2 1/3 pies amongst 4 1/3 people. In fact, now I've got even sense, this is a bit over 6 1/2 thirteenths. I can see that's just over half a pie per person. I can actually see what that one is. Whoa, that is a wonderful, wonderful move. All right, final move. Let's do something like 4/7 divided by 5/3. That is, I'm really doing disguise, 4/7 divided by 5/3. I want to see keep, change, flip happen to me. Okay, here goes. We've got 1 minute left. Let's see if the magic happens. And all we've got to play with is the properties of fractions we've identified, thanks to pies per student, pies per person, and running out of room here, but and any logical consequences of those we already know. All right, I'm going to be a mathematician. I don't like having 7s in a numerator. That seems terrible. Let's get rid of that. Let's make that go away. Let's multiply the top by 7. If I do that, I better multiply the bottom by 7 as well. Okay, that'll make my life easier. Great, so what do I got now? So this equals, I know I can cancel these 7s, what I was taught, but I justify that. I know the logic behind that. That's 4 on the top. Life is good there. Oh, but 5/3 times 7 on the bottom. I'm not liking that. I have a second problem. Bother. There's a second problem. But what don't I like about it? Well, I don't like having fractions in the denominator. I don't like those thirds there. All right, what do I say to myself? If you don't like thirds, make them go away. Just do a mathematically valid operation to make your life easier. Okay, I choose to do this property again. Let's triple the top and triple the bottom. That'll make my life easier because on the top I'll get 4 times 3. That's 4 times 3. I'll just keep the numbers. I won't actually do the arithmetic just yet. I'll keep the numbers there. And on the bottom, I know I'll get 5 times over 3 times 3. The 3's will cancel out, and I'll get 5 times 7 on the bottom. There it is. The answer is really 12/35. Okay, great. I've worked out dividing a fraction just by following my nose, which really was, I didn't like how things smelled there. I got rid of the 7s. I didn't like how things smelled there. I got rid of the 3rds, and I'm left with that. And if you look at that, what do we see? We see 4/7. There's still a 4 on the top, and there's a 7 on the bottom, 4/7. And we see a 3 on the top, and we see a 5 on the bottom. Oops, it was off the page. You don't see it. Whoa. It looks like I kept the 4/7. I changed things to multiplication, and I flipped the 5/3 to 3/5. The thing is, I'm never going to think that. I won't even remember KCF after this talk because it's not in my brain. My response is just do it. If you don't like 7s, make them go away. If you don't like 3rds, make them go away. Let's teach kids how to problem solve, even in fraction theory. It's not about fractions. If you really had to do these fractions, I doubt you'd ever really need to do them. I say just get out your I don't know, ask Siri. She'll probably do the arithmetic for you and give you a fraction answer. In this day and age, it's not about getting answers. If you just nut your way through it, which is the skill I really want to teach kids, when faced with a challenge, yes, have an emotional reaction to it. You're a human, you're meant to be human, things do look scary. but then take a deep breath and then follow your nose and make something happen. Fractions are actually a beautiful vehicle for teaching the confidence to handle problems in the world. It's not really about the content anymore. It's really about the confidence and the agency to be an effective citizen of the 21st century.